Speaker, who will be Quentin Gargan, as you mentioned before, from Ireland, from Voltsys. Thank you very much, Ken, and I hope you will follow us also, because I think there will be a lot of interesting matters for you as well here.
Thank you, absolutely, and thanks for listening. If you have any other questions, don't hesitate to get a hold of us.
Thank you very much. Well, Quentin Gargan, are you ready to go on now?
Is my screen on there now, is it?
You're on the screen. I can see you anyhow on the screen.
Oh, right. You should be seeing my screen. Are you not seeing my screen yet, no?
Nope. So I see your face.
Yes, this is the joys of actually doing this. I thought this was working. So I selected to share my screen.
Yeah. I think it's coming now. Here we are. Thank you. Please go ahead.
Certainly. Sorry. Okay, I think we have it working there now, do we? So my name is Quentin Gargan. I live in a beautiful part of West Cork in Ireland. This is my house here, which we built 20 years ago with straw bale walls. We had solar PV panels, which I would be embarrassed to tell you how much I paid for those. Solar thermal. We have a what was called a Proven 2.5 wind turbine back then. This is a Scottish-made wind turbine where the blades actually fold in and cone. It's probably the one remaining workhorse of a lot of turbines that were in the market at the time. We were lucky we bought one that actually survived in these West Cork winds. So just in terms of, I'm afraid following from Ken's wonderful presentation there, this is rather boring. I commend Ken on a very good and interesting talk there. I'm afraid he's a hard act to follow. In terms of the history of kind of taking a wind turbine and converting it to the grid, we had typically a turbine went into a short circuit break. You had a wind interface box, which was a rectifier and a dump load controller. So typically it would take in the AC from the wind turbine, rectify it into DC. It would contain smoothing capacitors to provide some sort of smooth DC into an inverter. And then if the voltage went too high, if the turbine went over speed, there'd be an IGBT would trigger a dump load resistor to keep the turbine under control. Those of you who are veterans of the industry may remember this little black box from Magnatech and then Power One, which was actually built as a wind inverter. If I'm not mistaken, somebody could correct me on this, but if I'm not mistaken, the early inverters were all actually wind models, and then they came up with solar versions of them as solar panels came down in price. Later on, an improvement was made to this. In this case, in both these cases, the power curve, as the turbine speeds up and the voltage rises, you want to extract more and more power. And you develop a power table which optimizes the turbine. And there's a lot of donkey work in that often doesn't get done by turbine manufacturers, where you actually record the wind speed and you see how well it works with the given table of voltage to power. And then you try increasing the voltage or increasing the power ratio and see if that improves or worsens the situation with higher wind speed. Anyway, the next evolution was that this inverter, the power curve, was based on frequency. So the wind interface provided a frequency-based power, provided a frequency signal telling the inverter what RPM the turbine was doing. And your power table was no longer voltage to power, it was RPM to power. This was an improvement because the power available from the rotor of a turbine is proportional to its speed and not necessarily to its voltage. So later on, ABB and Power One produced a different logic of system where the power table was stored in the rectifier. This is their 30 kilowatt unit or their 25 kilowatt unit. And it stored the power table and had the logic for the power management. And it also had some other useful features, the ability to disconnect the turbine if a turbine had a pitch mechanism and could be set free to spin free and had its own control mechanism. it could leave the turbine run open circuit if required. But the essential difference was that the power table was stored in the controller, and it sent a signal to the inverter, telling the inverter how much power to convert. And this was done with a very crude frequency table, just a linear table. At 50 Hertz was 0 watts, 150 Hertz was 30 kilowatts. So the essential difference here is that the power logic was in the interface and not in the inverter. Now, as Ken mentioned, the competition from solar PV gradually eroded the market for wind for companies like ABB. And at a time when we were ordering and delighted to order 2 pallets of inverters at a time, somebody else was on the other phone line ordering 3 container loads. And we ended up in the halfpenny place on a lot of inverter manufacturers. They were producing solar versions of their inverters, and these were outselling the wind ones by 10 or 20 to 1. So ABB decided to discontinue this wind interface, which was a bit of a blow to us at the time because we were selling these for a couple of different brands of turbine, and we had been producing our own rectifier controller for other functions at the time. And we decided to put into this a logic circuit that would do what the ABB unit did. It stored the power curve and it told the inverter how much power to convert. And that was a very successful product, continues to be sold to this day. But all the companies that were involved, all the major operators, I should say, that were involved in producing wind inverters all pulled out of the market within about a year. We lost SMA's Windy Boy, which is a real solid workhorse of an inverter because it had a transformer in it, which is quite useful in wind applications. We had the ABB discontinued its wind inverter, and Jinlong discontinued theirs as well. We responded to this by changing how our inverter works so that it could work with the mass-produced solar inverters. And this was quite a shrewder move than we thought it would be in some ways, because solar inverters are mass manufactured on such a scale that they're an awful lot cheaper than the wind models ever would have been. So we were able to work with solar inverters. We stored the power curve, and we have a microprocessor in our controller which stores the power curve, and it tells the inverter how much power to convert based on either the voltage or the RPM of the turbine. And this is managed by using the Modbus port on the inverter to disable the MPPT tracking and tell the inverter how much power to convert. So we brought out smaller versions of this. We brought out a 20 amp and a 40 amp unit for turbines in the 3 to 10 kilowatt class. And these work with the ABB, are now rebadged as FEMA range of inverters, the Uno DM range for single phase, and the Trio and PVS range for 3-phase. So we also, for companies that already had their own rectifier and dump load controller, we produced a small DIN rail mounted microprocessor that does the logic side of this. It stores the power curve, it reads the DC voltage. So there's connections in here for the 2 legs of the AC from the turbine, or for DC from the rectifier. So we know the turbine RPM and we know the turbine voltage. And the unit stores the power curve, and it communicates through Modbus with the inverter to tell the inverter what power to produce. So it also has a micro SD card plugged in here, which records the RPM, the turbine voltage, and what the inverter is doing. It's AC and DC current and voltage and information like that. So as happens quite often with turbines, unfortunately, if there is a breakdown or if there's a fault, it's very useful to have a data log on site of what the parameters were, and you can find that the turbine oversped or that something went wrong with the grid. So this is the typical circuit. We have a wind turbine, we have the AC coming into the controller rectifier, we take the DC into our logic controller, and we take a connection from the Modbus to 1 or 2 or more inverters. And as you know, with single phase inverters, if you have more than one inverter, you need a transformer on the grid side of all but one of them. So, and then on the rectifier controller, we've a 20 amp, a 40 amp, and an 80 amp model. We've been working with turbines between 3 kilowatts and 50 kilowatts. We've got some units working on 100 kilowatt units in Korea. So we rectify the wild AC to DC, and we have smoothing capacitors of various banks of capacitors that might be required to smooth, depending on the number of pole pairs in the inverter, in the generator. The amount of capacitors might increase or decrease. So it stores the power table or the power curve that's required for the inverter conversion. It overrides the maximum power point tracking of solar inverters, and it can control the inverter based on either a frequency or voltage-based power curve. We also use rather than a fixed dump load, we use a pulse width modulated dump load. So we have I suppose like a dimmer switch really on the dump load resistor that we can turn it up or down. And this becomes very useful in keeping the turbine under a more constant load rather than something that's switching on and off. It also, of course, provides a DC dump load during grid failure, but at that point, if we've lost the grid, we've lost our logic. So it's a hysteresis only dump load. We don't use pulse width modulation once the grid has failed. So it's got a little internal screen for providing basic information on what the turbine is doing. We also have an anemometer input, and that can be used for data logging. And that's particularly useful if somebody's building prototype turbines and wants to simultaneously log the wind speed as well as the turbine speed and the power coming out of the inverter. It enables you to more easily develop your power table or your power curve and find out what the optimum power curve is for your turbine. There's also a general purpose relay, which I don't think you can see up in the top right of this unit, which can be triggered by a number of different things, either over voltage, over speed, or over wind speed. And that can operate an external braking system, which can be either a three-phase dump load or a pitch mechanism on some turbines, or whatever other option a turbine may have for controlling over speed. And we're also working on developing intelligent restart options so that the turbine can know when to restart if it doesn't have an anemometer. I can answer questions on that if people are interested in that. Also, quite apart from wind, of course, hydro is also in the same boat of not having inverters available when all the major companies pulled out. And we're working on a system where the power curve can be optimized, where the controller can learn the optimum power curve for a hydro, because this is very different. You make a wind turbine and it behaves much the same no matter what site you put it on. The power curve is the same, but with hydro, every site has a different head height and has different characteristics. And so a self-learning power curve could be a very useful thing. We also provide Modbus on our board for external monitoring. This is a new feature that we're working with, but the protocols are available on request. And again, it provides a data log to the micro SD card, which can record 1 year of files recording the RPM, the turbine voltage, the inverter status, the wind speed. Turbine phase loss detection is something that we've found useful in post-mortems on wind turbines. We found that one of the slip rings had failed, or that something had failed in the turbine. I was running on 2 phases. It's something we can record. We're also working on something that shuts the turbine down in that eventuality, but that's quite a difficult thing to do. Now, so far we've worked on wind. With hydro, we're able to work with Solace and with other brands of inverters. With wind, so far, the only company we've found whose solar inverters have a fast enough response to Modbus has been ABB, or now rebadged as Femur. And we're able to read the wind speed, read the turbine RPM, look up the power table, tell the inverter how much power to convert. We're able to do that cycle 30 times per second. We found that other brands of inverters took 2 seconds to respond to Modbus commands, and that's far too slow for wind, but it is acceptable for hydro. So the advantage, I suppose, to working with a solar inverter is that the inverters tend to be cheaper because they are really mass produced on an enormous scale compared to what we could ever achieve in the micro wind industry. And they have, because they have such scale and they're sold internationally, the certification for most international grid standards is already on board the inverter. So you can buy it. The same model of inverter can work in Germany, China, Korea, Japan, North America, etc. In terms of off-grid sites, the traditional model, and the one that I have at my house here, is a low voltage turbine, a 24 volt in my case. You want to see the copper that comes off that thing. It was 70 mil copper. One of these days I'm going to dig it up and become rich. But for small turbines, a 48 volt system is not a ridiculous cable size, and this is an example of one company's offering where you're able to use lithium-ion batteries. The traditional turbines worked with a 48-volt battery, and you could sit there holding the system at 53 volts or 56 volts if it was bulk or flow charging into lead-acid batteries. Lithium ferrous batteries, which are now becoming more popular, need a little bit more control. It's a pity you can't see the right side of that picture. I'm right in saying you can't see the right side of that picture, but there is a hybrid inverter over here, a hybrid solar inverter and solar panels, and it manages the battery management system. And so this unit simply pumps in 48 volts to 53 volts DC. But it is a requirement that a switch within the battery or relay within the battery is able to put a brake on the turbine when the battery says stop charging me, that it actually stops providing energy. And that's an important requirement. Above 1 or 2 kilowatts, these low voltage systems have too serious power loss or require too heavy a cable. And the power conversion from 48 volts to 230 volts is inefficient. So for this, we revert to what we normally do. This is our standard grid-tied system with the controller, the dump load switch, the grid-tied inverter, and the logic to the inverter, feeding into a Jinlong or Victron or an Outback or whatever your preferred brand of inverter charger is, going into the AC hot out and AC coupled. Now, those of you who've worked with these systems know that when you go into the AC hot out of an inverter charger, you lose the charge control. So there's no brake on what goes into the batteries. So the inverter charger uses frequency shifting to change the frequency of the microgrid. And that sends a signal to the inverter saying to throttle back. And that system works quite well with ABB or FEMA inverters. They have the ability to recognize that. But here's the rub. When the inverter throttles back, you need some system that keeps the turbine loaded optimally. Otherwise, the turbine will speed up and in some cases will become a little bit noisy or whistly because it's no longer optimally loaded. So what happens here is that our controller detects the frequency shift from the inverter. The inverter brings the frequency from 60 hertz in the States or 50 hertz in Europe up to 51.5 hertz. And the inverter throttles back, and the controller responds to that by proportionally applying a dump load resistor to keep the turbine constantly under the same load as if the battery was flat. You can do the same thing in 3-phase using a controller and the ABB Trio inverter and take your 3-phase into 3 inverter chargers, and you have the same 3-phase grid that you would have had in a normal 3-phase setup. And the beauty of this is completely scalable. You can scale this with Victron, certainly, who we work with mostly. You can scale right up to 200 odd kilowatts of system. I'm going to skip that one because I think I'm getting low on time. Our controllers are all programmed by simply plugging a laptop into a cable that's supplied with the controller and the USB. There's no RS485 requirements or anything like that. And these are the kind of settings that you can adjust. You can have the dump load come on at 0 pulse width modulation at 400 volts and be 100% on at 500 volts or whatever you set it to. If you put in here what the dump load resistance is, then the controller knows how many kilowatts you've sent into the dump load in the last second, 10 seconds and 100 seconds. If you don't want the dump load to start at 0%, you can put in a figure here between 0 and 255 to have it come in. In this case, at 80, it's coming in at about 1/3 of full power. When it reaches 400 volts, it comes in with a bit of a bang at 1/3 of full power. These are settings for when the grid has failed. What the hysteresis dump load setting will be, it'll come on at 530 volts and off at 430. You got an over voltage limit that will set on a turbine brake or operate the relay and will operate the dump load permanently. And then you have a timeout on that in seconds as when you want it to revert to operating normally. If you have overspeed, over frequency for 1 second, you can have in this case, it's set up to 28 hertz for 25 seconds or 30 hertz for 2 seconds. And either of those situations will cause the brake to come on until the frequency has fallen for a period of X seconds. same thing with wind speed. You've got an upper and lower wind speed. So at 20 meters per second, it would shut down the turbine and wait until it was at 15 meters per second for 5 seconds or more before shutting down, starting up again. You have your power curve that you'll be familiar with, where at different voltages or frequencies, you increase the power takeoff from the turbine. You also have what is needed for the inverter is the ramp rate. In this case, the ramp rate, this is for a trio inverter, it's set to 50 kilowatts per second. So you can't jump around at a rate of more than 50 kilowatts per second. And then you have a monitoring tab if you have a laptop plugged in that you can see all of these different variables. I'll move to the next slide, which is, this is for where you have an off-grid situation where you have AC coupling. When the grid goes above 50 hertz, when it goes to 50.3 hertz, it starts derating the inverter. And at 51.5 hertz or 61.5 hertz in the States, it would have the inverter completely derated. So between 50.3 and 51.5 hertz on the microgrid, the inverter would be derating to prevent the batteries from overcharging. And that system, and the dump load would come on proportionally during that time to keep the turbine loaded as per the original power table that you have. Okay, so that's my 20 minutes worth. And if anybody has any questions, I'd be ready to hear them.
First of all, thank you very much. It was interesting. And as you mentioned, are there any questions right now? Then we'll take them.
Easy ones.
If not, there was some questions from Ken to Ken Visser, and we might take them up now. We will, when finishing these questions, we'll have a break for about an hour. So let's take them before we go to lunch, European time. There is from George. Pardon?
There is a question.
There is a question, yes, from Brent Somerville. And he asked, if you don't ask himself, I'll do it. What changes the frequency in response to the battery state of charge?
That is determined by the settings on either the back or the Victron inverter charger or whatever it is that you're using. SMA Sunny Island, sorry, is a third version of that, and all three have a system that when the battery is full, so it depends on the BMS of the battery. If it's a lead acid battery, it would happen after bulk voltage has been held for a period of time. If there's too much, if the voltage is rising too high on the battery, it would gradually raise the frequency of the grid, and that would curtail the inverter and hold the current going into the battery at the appropriate level. So that really depends on the relationship between the grid tie inverter, the inverter charger, and the BMS of the lithium ferrous batteries. Or it would depend on the voltage in the case of a lead acid battery, you know, the bulk voltage and the time it had been at that bulk voltage.
Okay, does it answer your question, Brent? I hope it does.
Yes, thank you very much. That was great.
Good. And then there is a question from George Sheedis that he's, pardon, yes? Yes, this is from the previous presentation to Ken Visser. He says, thank you for your presentation. And do you have any future plans for a larger scale? Any investors interested in the larger scale?
Well, thanks for the question. So that's a good question. And, you know, a lot of people have asked us, you know, can you scale this up? And theoretically, yes. Practically, that's a different story. In fact, we were asked down to Brookhaven National Labs in Long Island of whether you could even apply this technology to a large commercial turbine. And theoretically, yes. I mean, things work very well on the computer, but practically, I don't think there is some point at which it's impractical. I think it comes from, I don't know if you're familiar with the square cube law. But, you know, when you have something that depends, its function depends on the area, such as this, you know, the duct area is what drives the design, but the weight is a function of the third dimension as well. So you have a growing increase in weight of the duct. And if you can imagine some of the big offshore turbines, forget about the expense for the moment, but just the sheer weight of a structure to wrap around a rotor would be simply undoable. So I don't know how big you can scale it up. I personally think this is really kind of more of a small scale solution. There have been companies in the past that have tried different kinds of things. Certainly the history of ducted wind turbines is very colorful. You're probably familiar with the Vortex 7 that was tried out in New Zealand. There was a company, Flow Design, which then became Ogen or whatever, and they built, I think, 6 100 kW ducted turbines out in the California desert. And then mysteriously, they all got taken down. Nobody's quite sure exactly what happened. I mean, there are people out there who know, of course. And I don't know whether that was a structural issue or not. But at some point, the structure required and the support structure and the weight, which of course translates directly into cost, will outweigh the economic advantage. So, so the short answer is yes. I think you can go bigger. I'm thinking probably the most you could do is maybe a 10 kW design. I don't know if practically you could get above that from a practical point of view, but we really haven't explored that. I guess, you know, we're trying to focus on getting something that's actually, you know, viable at the scale we're at, and then we'll see where it goes.
Thank you. And then we have a last question from Emmanuel Dawn. I don't know if you will ask yourself, or otherwise I will read it here from the chat.
I think I just said thank you for the interesting presentation. Maybe it's the older question then.
Okay. Well, you don't go through Emmanuel Dawn, but as I understood, you have already raised your question and it has been answered. Is that right?
Yeah, everything's fine. I just want to say thanks.
Yeah. Any further? There might be one extra, then we'll take this. That's from Fritz Ock. You want to place it yourself, Fritz?
Yes. I would like to know what if there's a comparison between a ducted turbine and the extra cost and a bigger rotor. You can also have a higher yield by a bigger rotor.
Yes, absolutely. And we get that question a lot too. And so I don't have any specific numbers for you here. I'd have to turn you over to our one of the other fellows in our company for that. But you're absolutely right. I could get the same output from a bigger rotor. One of the interesting things that we're looking at, of course, is the efficiency of our unit. And so the advantage is not only can I have a smaller size rotor or a smaller visual thing, is that I could put it on a lower tower as well. And so to get the same kind of energy output. But no, I haven't done the cost. That's part of our project here with the National Renewable Energy Lab, is to take a look at that and what's involved with that. So no, absolutely. Good question. Good question.
Well, thank you very much. It's been a pleasure having you here, and I hope that you will follow us in the further conference. We'll take a break now, and it will have a duration of about 1 hour. We'll meet here 1:45 or sorry, no, we'll meet here 13:15 CET, Central European Time, but that's about 1 hour from now. So I wish you a good break. See you later.